Imagine a robot standing in a pristine laboratory. The floor is perfectly flat. The lighting is controlled. The objects it needs to manipulate are placed exactly where it expects them to be. In this environment, the robot can function with impressive dexterity. It can pick up a cup, walk across the room, and place it down without error. But move that same robot into a real home, and the situation changes entirely. The floor might be uneven. The lighting might shift as clouds pass outside. The objects might be in different places, or they might be cluttered together in ways the robot was never taught to handle. This stark contrast highlights the central problem facing the industry today. Humanoid robots are currently trapped inside a walled garden of controlled environments. They are designed for specific tasks within narrow parameters, not for the chaotic reality of the human world. To escape this confinement, we need to understand exactly what is failing. The first major bottleneck lies in the physical hardware itself. Current humanoid robots rely heavily on proprietary actuators and sensor suites that are optimized for stability in simulation rather than resilience in the wild. An actuator is the motor that allows the robot to move its joints, much like a muscle in the human body. In a factory setting, you can afford to have heavy, powerful motors because the environment is predictable. But in an unstructured environment, the power density of these motors becomes a critical failure point. The robot needs enough torque to handle unexpected forces, like a child bumping into it or a heavy object being dropped. But it also needs to be light enough to conserve energy. Currently, the battery technology and motor efficiency required for all-day operation outside a charging station simply do not exist in a package small enough for a humanoid form factor. Furthermore, the sensor fusion required to navigate this world is often insufficient. Robots rely on a combination of cameras, LiDAR, and inertial measurement units to understand their surroundings. In a lab, the data streams are clean. Outside, dust, rain, and glare introduce noise that confuses the algorithms. The robot must process this sensory input in real time to make decisions. If the robot cannot distinguish between a shadow and a hole in the ground, it cannot walk safely. This is not just a software issue. It is a hardware limitation where the sensors are not robust enough to handle the variability of the physical world. The industry has spent years trying to force current hardware to work in new environments, but the physics of the situation remains the same. You cannot run a simulation forever and expect the physical hardware to behave perfectly when the simulation ends. This brings us to the second layer of the problem, which is the intelligence driving the hardware. For years, the dominant approach was to program robots with rigid rules. If the robot sees a red box, move left. If it sees a blue box, move right. This works for a specific task, but it fails when the task changes. A robot that can fold laundry cannot necessarily make a bed, and a robot that can walk on asphalt might struggle on gravel. To become generalist agents, these machines need to transition from static, rule-based designs to dynamic, AI-driven frameworks. This means leveraging generative artificial intelligence and large language models to enable complex reasoning. Instead of following a script, the robot needs to understand the intent behind a command. It needs to know that if you ask it to make coffee, it must find the machine, locate the water, and understand the concept of brewing, even if it has never seen that specific coffee maker before. However, simply plugging a large language model into a robot is not enough. There is a critical issue known as catastrophic forgetting. When a robot learns a new skill, it often overwrites or degrades its ability to perform previous skills. This is a massive barrier to deployment. If a robot learns to open a door, it should not lose the ability to carry a tray. To solve this, researchers are proposing a framework called tree learning. This is a multi-skill continual learning system designed to prevent catastrophic forgetting. It allows the robot to branch out into new skills while retaining its existing capabilities. The goal is 100% skill retention. The robot accumulates knowledge like a human does, building a library of abilities that it can draw upon as needed, rather than starting from scratch every time it is reprogrammed. This requires a shift in how we train the models, moving away from single-task reinforcement learning towards systems that can handle multi-skill continual learning. But the intelligence is useless without the right physical form. We had been trying to copy the human body exactly, assuming that because humans have 2 arms and 2 legs, robots must too. This assumption is flawed. The human body is the result of millions of years of evolution, optimized for survival, not for efficiency in a factory or a warehouse. We need a paradigm shift in body control co-design. This means the physical morphology and the control strategies must be jointly optimized. The hardware and the software should evolve together. If the robot is designed to carry heavy loads, its center of gravity and joint placement should reflect that, rather than mimicking human proportions for aesthetics. We need to stop treating the robot body as a fixed platform and start viewing it as a dynamic component that is tuned to the specific algorithms controlling it. This allows for biological adaptability rather than relying on fixed, manually engineered bodies that are brittle in the face of unexpected stress. Finally, we must address the social and ethical dimension of deployment. This is often referred to as the Humanoid Factors framework. As robots move into human spaces, the priority shifts from pure performance to safety, trust, and intuitive interaction. A robot that functions perfectly in a lab but terrifies the people in the room is a failure. The robot needs to communicate its intentions clearly. It needs to understand social cues. If a person steps in front of it, the robot must know to pause, not just because of a collision sensor, but because of social norms. This requires integrating natural language cognitive architectures that enable high-level reasoning and long-term planning. It is not enough for the robot to react to a command. It must understand the context of the environment and the people within it. There is a significant knowledge gap remaining regarding the practical scalability of simulation to real transfer. This is the process of training a robot in a virtual world and then deploying it in the real world. While simulation is powerful, the physics engine can never perfectly replicate the friction, wear, and tear of real materials. There is a critical bottleneck here where current hype may lead to a bubble burst if developers cannot solve the fundamental challenges of locomotion and manipulation stability in real-world physics. We cannot rely solely on simulation. We need robust testing protocols that expose the robots to the chaos of the real world without breaking them. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.